Welcome to Study Loop.
So we have the following system here. We have two stars orbiting each other. So they're each orbiting their common center of mass, so right in the middle. And so then there's a distance or radius r between that and each star. So then we have star 1 and star 2 each going around the center of mass in orbit. So first we're asked to find what the gravitational force of one star and the other is. So that's none of this orbit stuff matters for that. That's just two objects. So we can just say gravitational force, as always, is just the gravitational constant times m1, m2 over r squared. That's just in most general terms. And so now we're told the stars are identical, so we can just say they each have mass m. So this would be g, m times m is m squared. And then their distance between each other is actually 2r, in this case, a diameter. So as we've defined r here, then it looks like we would have 2r, and that would be squared. So this will be g m squared over 4r squared. Part B now asks us to find the orbital speed of each star, as well as the period. So you might be tempted to use this equation we've used a ton this chapter of v equals 2g over r for the velocity. I have 2, but this does not work here, so don't look at that. Um, so this works when you have an object orbiting um, just around 1, but because it's orbiting a center of mass, this equation doesn't quite apply since there's not like actually an object there. It's just the common center of mass of these two things. So probably the easiest approach we can take is the fact we know each object is moving in a circle, and we know the only force acting on it is this gravitational force. So we can just say then that this gravitational force is creating a centripetal force on each star and set it equal to that. So on a given star, the gravitational force must equal the centripetal force. And so we have our gravitational force of gm squared over 4r squared. And the centripetal force is mv squared over r, most generally. And in this case, the radius of the circle is just going to be this capital R. So we have to be really careful with all these R's and think about what they actually mean. So here, though, other cases R has been separation, so we wanted 2R, the full diameter. Here, R refers to the radius of the circle of the star in circular orbit. So we just want 1R here. And so now we can just solve for V here. So one of these M's goes away, that R and that square goes away. And we get then that v is just the square root of g m over 4r. And finally, part C asks us how much energy we would need to separate the stars to infinity. So we almost always want to set these up using conservation of energy. So we say the initial energy, so initial potential plus initial kinetic. And a lot of times we're doing initial energy equals final energy, but in this case we're asking how much energy we need to separate the two. So really what we're saying is how much work do we have to add in to the initial energy of the system in order for it to become this final state where the two masses are infinitely far apart from each other. So now it's this W that we want to find that tells us how much work we have to do. So when we say that the two stars are now infinitely far apart, that means that the potential energy is going to be 0 between the two. There's a divided by r in that term, so you can see mathematically it'll go to 0, and just kind of conceptually, if they're infinitely far apart, they're applying no force to each other, and so there's no way for them to kind of add energy to each other. Um, and then the kinetic energy, it's a little unclear from how they phrase it, but typically what they're asking for is the minimum possible amount of energy we would need to separate them. So then we're usually thinking that the kinetic energy would be 0 in this case too. any additional kinetic energy the two stars had when they're separated out to infinity is just going to be more work we have to add in. So if we want the least possible amount of work, that would be that they're put at rest when they're infinitely far apart. So another way of kind of thinking about that is that we're also using the initial kinetic energy they have to move them apart. So we're saying they have some sort of kinetic energy here, and then we're presumably adding in work in the form of kinetic energy so that eventually they kind of have their escape velocity from each other and then slowly move away out to infinity. And the whole time their velocity is becoming slower and slower and slower until eventually, or not exactly eventually, but theoretically eventually, they're infinitely far apart and then they have zero kinetic energy. So the final energy then is zero. We say our initial potential energy is negative g, and then that will be m squared, so m1 times m2, and then over r, but r the separation between the two. So that would be 2r. And then we have the initial kinetic energy, so plus 1/2 mv squared for a given star, but we have two stars, so we got a 2 there. Oh, mv squared. And then plus the work we're doing, and this whole thing needs to equal 0 since both of those terms are 0. So we can get the work by itself then, and that should be equal to g m squared over 2r, and then minus m v squared, since that 2 and that 1/2 canceled out. So now we can substitute in this v that we'd found over here. So this equals g m squared over 2r minus m, and then this v squared will be gm over 4r. And so now we can see, we can write this as m squared. So we have gm squared over 2r minus gm squared over 4r. So that's going to then just equal gm squared over 4r. So we can get that by, rather than writing this as 1 over 2, as 2 over 4. So 2 over 4 minus 1 over 4 gives us 1 over 4.